Hope you all can hear me clearly. And I assembled a set of slides here which kind of highlight how generic models for DER resources, which are primarily inverter interface, have evolved over the years. And the basis for most of this work is to remember that our goal is to represent a large number of these DER resources in large scale positive sequence time domain simulation. And in doing this, people realized very early in the game that the converter is the main interface between the source of power and the network. And I'll give you a brief history a little bit later, but I think the first set of these generic converter models had already been developed for wind turbine generators. And this specific model is primarily used even for interfacing solar PV units in terms of doing transient stability simulations. And in these early models, the converters were largely represented as current injection devices, which would inject the required current into the network. And behind this framework, the active and reactive current commands are issued by appropriate control blocks. And the model basically receives individual current commands and injects a complex current into the network. This was the basis. And this is the framework which is described here. You see there is the IQ and the ID currents, which are IP command and IQ command, which are injected. And then you have some voltage, high voltage reactive current management and a low voltage reactive current management. Basically, what this does is, in this particular case, it controls the current limit. And the time constants in the model that I just showed you essentially represent the switching of the solid state switches within the converter. And the behavior of few limiting devices is also built into the blocks, the most essential ones. And this low voltage power logic, which I showed you on the previous figure, uses the terminal voltage magnitude to control the upper limit on the active power injected. And if the bus voltage magnitude of the converter does fall below a certain threshold, say because of a disturbance, the LVPL block will reduce the upper limit as shown in the characteristic, which is basically a linear characteristic. It varies within low voltage magnitude values, and the current limit is then varied in a linear fashion. And if the voltage magnitude falls below the lower bound of the range, the active current limit is made 0. And so in this normal operating voltage range, the LVPL block does not actually affect the active current limit. It's only when we have these situations where we have disturbances and low voltage. And one of the key features of this model was that all the elements and things in this LVPL block can be set by the user. And the basis behind this was, for planning purposes, WECC wanted to create a generic model which could accommodate the parameters and settings from multiple vendors. And that's one of the things we are attempting to kind of continue, follow, and build upon within UNIFI itself. So this was the way they built flexibility into this generic model. And this also has two algebraic current limiters present in this block. This high voltage reactive current management section reduces the reactive power injected if the terminal voltage rises above a certain user device limit. And the rate at which the reactive power is ramped down in this case, again, can be set by the user, because this is something which is specific to the manufacturers. And the low voltage active current management section basically reduces the active power injected if the voltage magnitude falls below a certain threshold. And this is kind of shows you a detailed setup of what the logic looks like. And you basically see that In this figure, IQ command is actually created here, and IP command is actually created here. And you notice that the terminal quantities which are fed is terminal voltage is fed. And I'll show you in a few minutes. There are three options where you can give different specifications for the reactive power side. So the control model basically is responsible for generating the active and reactive current commands for the converter model. So basically what I showed you here in this slide, IP command and IQ command, is what is fed into this converter block. So behind this is the control block which sits within the stability simulation software. And then at every time instant when we do the network solution and we update the voltages, the updated voltages are fed in here. So the control model is primarily responsible for generating the active and reactive current commands for the converter model. And as I showed you, the bottom section of the model shows how to calculate the active current demand, and the reference active power which is provided can either be set by the user using an external user written dynamic model, or you can simply use the value scheduled in the power flow. This feature provide the flexibility for the inclusion of even a governor type model to set the active power. So this is referred to as WECC's REECA model. And I've given you the reference in the slides. There is a wide range of background material available in this site, in this particular site. And then added to that, a lot of actual on-site testing of this model compared to measurements has also been done. So this model is a kind of a very reliable model and worked very, very well. And this is what I was talking about in the IQ command case prior to actually doing all the manipulation with the terminal voltage. You can have three different settings for the reactive current command. You can either have represent a solar farm VAR controller. This is an emulator for the VAR controller for the solar farm. Or you can regulate power factor, or you can basically supply user-defined reactive power. So these are the three options available because different plants have different ways of controlling reactive power. And basically the converter current limit block ensures that all current commands are within certain limits. So this is how this was set. So the basis for this original model that I showed you, that this idea of representing this in a very simple structure came out from a very classic paper which was presented at an all-day panel session on wind generator modeling at the 2003 general meeting in Toronto. So like we are in COVID times now, I was telling Duncan just a few minutes before this webinar started, the 2003 general meeting was dominated by the SARS epidemic. So it was not we did not have the usual attendance, but this was one of the most exciting sessions there. And this paper made a lot of headlines because this was the first time where people had actually been able to create a suitable model for a doubly fed induction generator based wind turbine model. It was a very simple model appropriate for bulk power system dynamic studies, and very clearly stated that this was purely for positive sequence phasor domain, time domain simulations. And the analysis primarily focused on how this distributed energy resource reacts to disturbances, for example, faults on the transmission system, and how it impacts the transmission systems. So as a result of which, in this model, the very fast dynamics associated with the control of the converter basically have been modeled as algebraic approximations of their response. And the reason for this, the analytical reasoning behind this is that the fast transients associated with the power electronic devices would have settled in the time frame of interest It's in time domain simulations, that is in transient stability simulations, which is primarily examining the electromechanical transients. So that was the basis for how these models were developed. So given that, the early GE work was then followed up by more detailed efforts conducted by an IEEE Power System Dynamic Performance Committee Working Group. And these three references that I've given here basically give a lot of background into what followed this original GE work. A series of first generation models were created. These were then later updated, and now at present they have a set of second generation models. And quite a bit of validation of these models by using actual measurements. That's one of the things which stands out among the work, various pieces of work done by this working group. And then the ability to provide these generic stability models for both defig and full converter wind turbine generators is another aspect of this model. So they have presented work in various fora, and actually provided a lot of input from manufacturers who allowed them to actually do some testing with the actual wind plants and compare the response to what these models provided. So just keep in mind, this is one way of validating models. The other way is, for very large systems, it's very difficult to actually validate models by actual measurements or conducting stage tests. Not everybody allows you to do these stage tests. So what people have done is looked at isolated portions of the system and then model that system in great detail using EMTP models, and then verified these positive sequence models in comparison with the performance of these detailed, well-accepted EMTP type of models. So that's another way of testing or validating some of these models. So the model that I just explained on these previous set of slides has been tested on an actual system, and the testing was actually done on a strong network, electrically strong network, and hence this constant current source model actually worked very well. And so this paper is a recent paper. What they did was they did a frequency response test showing simulations versus measured response in both the active power and reactive power of a solar plant. This is a fairly large plant, about a 23.5 megawatt PV plant. And you can see that in all these figures that I show you, the simulated plots actually track the measured plots exceedingly well. There's very high accuracy in all of these plots that I show you. So here is, they change the reactive power reference. It's a step response. Everything is stable. There is a sudden step response. And then you see the measured response in the reactive power output and the active power output. The scale is very small. So you see, it looks like this deviation is large, but in fact, the deviation is very, very small. And the same thing with the change in voltage set reference. There's a step down, and again the tracking is excellent. So this kind of testing has been done quite quite a bit these days, wherever available. And this is another under frequency response of a 250 megawatt plant, showing the simulation versus the measured response in megawatt and megawatt. And then again, you see both the active and reactive power actually. So this is under frequency. So you notice the active power increases, and then it meets the sudden increase in required, and then actually settles down to the value after the frequency settles down. So this is one case with, and this is an over frequency case, and here you notice the active power actually drops. So you notice the close resemblance of the measured response with the simulated response, and that is how they verified the efficacy of this particular model. So coming to how this work evolved, so the control model that I described previously works very well as per design and specifications, but it is quite complex. You notice the fairly elaborate control block. And in systems where there going to be significant penetration of PV resources, there was a need for a simpler control structure, bearing in mind that the stability of the system hinges upon the interaction of these controls with one another. So, and this model that I talked about earlier does have problems with network solution that during the time domain simulation, in cases where the electrical network is weak. So with this objective in mind, our group at Arizona State University kind of worked upon a design or a development of a model, which I will discuss next. And these are two important references. The first paper actually describes the development of the model and the testing of its validity. And as I said, one of the ways of validating this was we used fairly detailed inverter model in EMTP domain, and then verified our positive sequence model against that very detailed inverter model simulated in Plex. And Plex is a software which the power electronics people use quite extensively. And the second paper, which appeared in the PSCC in Genoa, Italy, actually does large-scale simulations using that particular model. And I will kind of discuss some of those results. So this is a very simple model. This is the reactive power controller and the active power controller. And what we did was in both of these controllers, we actually built in a droop. This droop, what we envisioned was basically that if you compare a synchronous machine, which is replaced by an equivalent inverter interface resource, this droop would be the same droop that would have been provided on that synchronous machine's governor. And this one we chose appropriately so that if there are multiple inverters at interconnecting to the network at a given bus, they would then appropriately share in the reactive power control and not fight against each other. So that was the idea of introducing these two groups. So you notice that the effective active power order on the previous slide is a combination of the power set point and the active power droop coefficient. And the reactive power order is obtained from the voltage error along with the reactive power droop. And the QV droop is instrumental basically in obtaining stable operation, as I just said, that because the multiple converters connected to the same bus. And so we denote the active power droop as RP and the reactive power droop as RQ. So in this model, we have also imposed limits on the maximum active and reactive power and minimum reactive power deliverable. And in choosing these limits, we have assumed that the converter can withstand an instantaneous MVA of 1.7 times its rating after talking to many inverter manufacturers. Further, we arbitrarily assumed at a terminal voltage level of 0.75 per unit, the minimum operable power factor is about 0.4. And this is from some practical examination that we did. And as the voltage dips, the limit of the converter control will change to allow for more reactive power to be delivered while curtailing the active power. So this was like a full 4-quadrant inverter. That's how we represent it. And the converter's interface to the network is modeled as a controlled voltage source rather than a current source in the original model, because the converter is basically a controlled AC voltage source with a voltage source on the DC side. And so we modeled this as a Thevenin source with the following D-axis and Q-axis voltages. And that's how we interfaced the model with the network. So here is the network solution, and that's how we interface this model with the rest of the solution. And as I said, the way we validated this model was through an EMTP type simulation on using Plex. And second, this first reference actually shows you the validation of that particular model. So what we have done is we have actually, after doing this validation, we wanted to test how this inverter model performs. And we tested it on a full-blown WECC model. And in this particular model, what we did was all generators within the WECC, excepting those that were doubly fed induction generators, wind turbine generators, and type 2 wind generators, were replaced with inverter interface resources. There are a few type 2, there were quite a few doubly fed, but we left them as it is. And then the droop coefficient RP for the active power was chosen to be same as that of the original governor. And what we did was we purposely built some headroom into the way these inverters operated. So the rating of the inverter was specified as the turbine rating of the original generator, which is usually higher than what the generator would be operating at. So as a result, the plants typically operated below this rating. And as a result, all plants had a certain amount of headroom. And I'll show you some large scale testing on these devices. We tested it on a number of different types of disturbances. We had loss of generation, we had significant short circuits. We also had closing and opening of transmission circuits. So we have done a wide variety of testing on this particular model. And the results depict in this particular model, what you'll see is that this model with two droops that we have, one in the active power loop and one in the reactive power loop, and allowing for this headroom, to a certain extent captures the grid forming ability of the system, and the system stays intact for even the most serious contingency in the WECC, which is a loss of two large generating station, two large generators. They are at the same generating station. It's a huge generating station with three large generators, and the loss of 2 units is considered to be the worst disturbance. And what we have done is we have actually monitored the WECC performance at various locations at 5 different key buses. And the 5 generating units are spread across the system just to see how this would perform. This model that we developed, we wrote it or described it as a user-defined model within GPSLF, which is a positive sequence time domain simulation software widely used in WECC. And this is what happens. The 2 generators which were lost, the sum of their generation was about 2,800 megawatts. And this is what happens when you lose them. You still notice that the 5 locations that we are monitoring, all of them remain fairly intact, well synchronized, and the relative bus angle does not deviate from very significantly from what it was, and the system kind of settles down to a new operating condition very smoothly. And this is what happens to the frequency, because this is a frequency is the variable of interest. The frequency deviation is not very significant. The system reacts very well, and the frequency actually settled down quite fast to a new value, because there is still significant loss of generation, and whatever was the headroom did not kind of compensate for this large amount of generation lost. And then you will notice that we also monitored the voltages at these 5 buses. The voltages drop, but they are well within specified limits of 0.95 per unit, which is what is required within WECC. Then comes the question, where did this recovery come from? And so what we have done is we have kind of looked at the actual flow from Southern California, Central Northern California, the Northwest in Canada. So you notice with this setting of this droop and allowing for headroom, basically, we had a total pre-disturbance active generation of this amount. The post-disturbance active generation was this amount. So when we do the careful analysis, 86.5% of the lost generation due to the loss of those 2 units is recovered through droop control. Then because you notice there was a slight drop in voltage, the remaining 13.5% of the lost generation is recovered through voltage dependent loads. So basically, the system kind of reacted, this control reacted very well to the changes in the system. The surrounding areas supported the area in need very actively and flow all the way from the Northwest through Northern California, and Southern California was able to meet the requirement. And this gave us a lot of confidence in this particular model. And this model, which we kind of developed as a part of a PSERT project, and the person who was a student working on this is Deepak Ramasubramanian, who is very involved in this consortium. This was adopted by WECC as the REGCB model. But one of the things we were not fully comfortable with was in this paper, we had not incorporated an inner current loop. So we kind of evolved this particular model by adding an inner current loop. And that is actually the results of that are described in this 2018 PSCC paper. And to the original model, we augmented the reactive power loop and the active power loop with this inner control for both the IQ and ID respectively, and tested it on the same system. And then again, you see, we in fact get a much better frequency control than we had before. And the voltage magnitude after the significant drop, we are able to control that into much tighter limits. And this model that we developed with the inner control loop has been further improved to include a phased lock loop by WECC. And this is now referred to as REGCC. And this is a model adopted by the WECC. And this REGCC model is described in this particular paper. It appeared in 2020. And you will notice that there are a lot of similarities to what we had. And here are the PLL loops which are included. So there is, you will notice here that in the network solution, you have to evaluate the current appropriately. And I've just given you an idea of how we do that. And this is the positive sequence representation of how the PLL is implemented. So it's implemented in this case using both the terminal voltage and the terminal current. So Deepak and his colleagues have actually tested this on a portion of a network in a real transmission footprint with the addition of several hypothetical renewable energy resources that are in the interconnection queue. And the system has about 119 buses. There are 3 equivalent sources representing the external outside system and the studied area, and 9 renewable power plants. And all of these are modeled as type 4 wind turbine generators in voltage control mode. with reactive power priority during low voltage ride-through conditions. And the total capacity of this system is 894 MVA with a total renewable generation of about 665 megawatts. And here they model the all 9 renewable resources with the RECA electrical control model, which I showed you earlier. And I've given you some typical data that they use. And what they have done is they have looked at the performance of the system just before critically clearing a fault and just after critically clearing a fault to see how this model would perform. And in this case, again, the positive sequence model that they have developed is tested with a fairly detailed PSCAD model. And what you notice here is I've shown you various plots from the same paper that I mentioned. They have looked at the frequency and angle of the phase lock loop of a particular turbine generator from the positive sequence model and point on wave simulation when the fault is cleared 1/8 cycle before critical clearing time. So that means the system is stable here. And you notice that the positive sequence model actually maps what the full-blown PSCAD model does quite accurately. And then this is the case where the system is cleared after critical clearing time. And even in this situation, you notice that the positive sequence model is quite accurate in capturing the performance of the phase lock. So what we see there is that in these models, the fast control loops in the modified positive sequence model are able to represent the transient behavior seen from the detailed point on wave simulations for both the stable and the unstable case. And the model that has been developed adequately captures the detailed dynamics and provides confirmation of the model development. The model is not manufacturer or vendor specific, it's generic. And it basically, and if manufacturer specific details are provided, the model can be readily modified. So I don't think that is a limitation in any of these models. And the model has the ability to represent grid forming inverters in large systems. So I think the bottom line is that with these new positive sequence models, it is possible to simulate 100% inverter interface system, just of the two types that we showed you, the WECC case, which is that has about close to 19,000 or 20,000 buses, 3,300 generators, and it's a full representation. All the nonlinear load modeling, all of that is represented exactly as is. So with that, I will stop here. I've kind of given you an overview and open the floor for questions.